Hello. In my last video, I talked about how the tides worked in our oceans, but the forces that do that do other things as well. And in particular, they're responsible for what's called tidal locking, which is the process that's caused the moon to stop spinning to the extent that it's always showing us the same face. So we'll look at that, and we'll also look at why Mercury's day is twice as long as its year, which is an interesting phenomenon caused by the same effect. So let's get started. So it's all about gravity, of course. So let's recap what we know about gravity. Follows an inverse square law, which means that the force between two particles is proportional to the two masses and inversely proportional to the square of the distance between them. And that causes two objects to orbit their common center of mass moving in ellipses. If you've got two things like this, they're not orbiting one another, they're orbiting their common center of mass, and they move in ellipses, not necessarily circles. It's important that this field is not uniform. So when we teach gravity at A level, for example, we tend to think of it as a uniform field pointing straight downwards everywhere and the same strength everywhere. Well, it's not like that. That will not do in this situation. In particular, it means that the effect on a body of gravity from somewhere else is not equivalent to a single force through its center of mass. Okay, now when we looked at the tides in our oceans, we saw that this was the force field that causes them, these forces around on the ocean. But those forces don't just apply in the ocean. Every particle in the Earth experiences a force just like that. So let's look at that. So here we are. Here are the forces on every particle in the Earth. They're weaker in the middle and stronger at the outside. They're pointing towards and away from the sun or the moon and inwards at the sides. And like the tides, it depends on the phase of the moon. So they're weaker at half moon and stronger at full moon and new moon. Now, unlike particles in the ocean, the particles in the solid Earth aren't going anywhere as a result of these forces. So what does happen? Well, the Earth gets slightly rugby ball shaped. There's a slight squishing of it, so that if you're standing here, you're about half a meter further from the center of the Earth than you are when you're there, because the Earth's spinning, so that bulge is sort of moving around the Earth. So when I say you're further from the Earth, center of the Earth here than here, that depends on the phase of the response, doesn't it? Whether it's bulging that way or that way. So remember when we looked at the tides, we asked whether the bulge of the oceans was towards and away from the moon like this, or out of phase like that. And we concluded in the end that they were out of phase like that, because, well, this is a tsunami racing around the Earth, and the natural speed of tsunamis is quite slow relative to the moon, which is forcing it to get right around the Earth in 24 hours. And so for the response is out of phase. And so we have the same question here. Is the bulge like this in phase, or is it out of phase like that? So let's go back to the mathematics and remind ourselves how that works. So this is what's called the forced oscillation equation. This describes any oscillator that's forced, like a pendulum or like the Earth being squished. So omega naught is the natural frequency of the oscillator, and omega is the frequency with which we're forcing it, and K here is the damping, it's the amount of damping. So green is the driving force and blue is the response of the system. And I've set it up here with very low damping and with omega being smaller than omega naught. In other words, we're forcing it slower than its natural frequency, and the response is in phase. And if you apply some damping, it delays the response a little. And a reminder, in the case of the tides, the response is out of phase when we're forcing it faster than its natural frequency. So let's go back to here. What we have here, of course, let's go back to this one, is it's not a tsunami, it's a seismic wave rolling around the Earth. Now, how fast do they travel? Well, we're talking about the really deep seismic waves. There are several sorts, aren't there? Surface waves and deep waves. And we're talking here about one deep in the body of the Earth. And they travel amazingly fast. They get right around the Earth in about an hour or so. So the response is definitely in phase. We're forcing it much slower than its natural frequency, but delayed slightly by the damping. So here we are. Here's the Earth spinning. Here's the moon. Now we'll change the frame of reference a bit so that the Earth's stationary and the moon is orbiting it, and put the bulge in. So now we have a bulge in phase, more or less pointing towards the moon, but delayed slightly by damping, by friction. So the bulge is slightly to the east of the moon. So what's the effect of that? Well, these forces aren't quite the same. This one's bigger than that one. So the force on this bulge is slightly bigger than the force on that bulge. And the effect of that is that there's a slight torque on the Earth, a slight twisting force that way. And if we return to the previous frame of reference in which the Earth is spinning, you see that the sense of this torque is the opposite sense to the one in which the Earth is rotating. In other words, this torque is slowing the Earth down slightly. And it is slowing down just a little bit by that amount. Right, now then, it's a fairly easy exercise to see that the effect of the bigger body on the smaller body is much, much greater than the effect of the smaller body on the bigger body, which we've just looked at. And of course, the moon has stopped spinning altogether to the extent that it's facing us all the time. It's tidally locked to us. And in fact, all the moons that are big enough to be round in the solar system are locked to their planets. But Pluto's an interesting example. Actually, Pluto isn't technically a planet anymore, is it? But Pluto has a moon called Charon, and they're about the same size. And in fact, they're both tidally locked to each other. They sort of go around looking at each other like this, which is quite cute. Right, now it's not just planets that can slow moons down. The sun can slow planets down. And in fact, it's slowing them all down. The most interesting case is Mercury, because it's a good deal closer to the sun than anything else, and it's also pretty small. So the tidal forces there are pretty big. So here's Mercury. Looks a bit like the moon, doesn't it? In fact, it's not much bigger than the moon. So in order to understand what's going on with Mercury, we need to look a little bit more carefully at the mathematics involved. So we'll stick with the Earth-Sun system for the moment. Here's our little tidal force here, which is the difference between the gravitational force here and the gravitational force here. Now, the gravitational force is this. This is the inverse square law that we've met before. So we can calculate this difference as the derivative of this with respect to big R times, well, minus little r. There we are. And the derivative of this is minus 2r to the minus 3. And so here we have the formula for the strength of the tidal force. And notice that it's got its inverse cube law in it. So tidal forces get bigger as you get closer to the sun, much faster than gravitational forces do. So now let's look at Mercury's orbit. Mercury's orbit is somewhat elliptical. This doesn't look frightfully elliptical, does it? But it's much more elliptical than most of the planets. So this is the center of its elliptical orbit, and this is the sun, one focus. So of course, the center of mass of the Sun-Mercury system is pretty much the center of the sun, because the sun's millions of times heavier than Mercury. Right. So in fact, Mercury really ought to have stopped spinning by now. The tidal forces are so strong that it's got no business not to be tidally locked to the sun. But it's this elliptical orbit that causes that. So let's look at this right. In fact, it stopped slowing down at the point where its day is twice as long as its year. So let's see what that means. So I've stuck a flagpole here in Mercury at midnight at perihelion, when it's closest to the sun. So let's run through a year. So get half a year, it's sunrise. Okay. Got once round, it's midday. Go round again, and it's midnight again. Now let's look again around midday. Watch that flagpole. It goes up through the sun, then it goes down through the sun, then it goes up through the sun again. And why is that? That's because it's closer to the sun round here, and therefore moving faster. And of course, it's spinning at the same rate all the time. So the effect of this is that if you were to stand on the surface of Mercury around noon, around here, that the sun would go backwards in the sky for a while. And the effect of that is that tidal torque that we examined which is normally slowing Mercury down, is actually speeding it up round here. And it turns out that's enough to hold it in this resonance where its day is twice as long as its year. It doesn't look as though it ought to be, does it? Because it's not doing that for very long. But notice the eccentricity of the orbit. So it's about 1.5 times further away here than it is here on this scale. That's 4 squares and that's 6. 1.5 cubes is 3 and a bit. So the tidal torque is 3 and a bit times more here than it is here. And that is enough to hold the thing in this resonance where its day is twice as long as its year. And it's going to stay that way. So there we are. There's tidal locking and why Mercury's day is twice as long as its year.